Hey everybody. In this video we're going to look at how to use StatCrunch to do some probability calculations based on the binomial distribution, the Poisson distribution, and the geometric distribution. So hopefully you've already watched videos on how those distributions work and how you know when to use which distribution. But I'll go over a little bit of how to know which one to use as we go through these problems. So let's take a look at some of these. Here's our first problem. It says, according to a Gallup poll, 60% of American adults prefer saving over spending. A simple random sample of 50 adults is chosen. Find the following things. Okay, so we want to find these probabilities here. Now, what have we got here? We've got, we have a probability that, well, we have the percentage of American adults that prefer saving over spending. Well, that means the probability, if we choose a single adult, what's the probability that they choose saving over spending? It's 60%. So what that means here is that I know that the probability that a single person has that preference is 0.60. All right, so I got my probability. And a simple random sample of 50 adults are chosen. So our sample size is 50. So we're choosing 50 people, and for each choice, the probability of success that we chose one of these people is 0.6. So whenever you have a fixed number of trials, we're choosing 50 people, and each trial has a certain probability of success, right? That's a binomial distribution, supposing the trials are independent, right? And so that's the one we're going to use here. So the first question is, let me just write that down, binomial. Okay, the first question is asking what's the probability that 25 adults in the sample prefer saving over spending? In other words, what's the probability that we get 25 successes? All right, so our first question here in part A, it's asking for the probability that X equals 25. Or sometimes they would just write this, the probability of 25, right? Either way, you may see it written both ways, right? So let's go find this. So what we're going to do is we're going to go to StatCrunch. Here we are. We're going to, after we're greeted by these friendly faces here, we'll open it up. And we will go to the following thing. We're going to go to Stat menu. We're going to go to calculators. And which calculator do we want to use? Well, these are all the different distribution calculators. Look at them all. But we know which one we want. We want binomial. So I'm going to choose that one right there. Okay? Now, what do I do with it? Well, I put in those parameters we were just talking about. So we said that, there we are, P is 0.6 and N is 50. Let's put that stuff in here. P is 0.6, N is 50. What else were we being asked? Well, we were being asked to find the probability that X was equal to 25. All right, well, that's what I'm going to put over here. I'm going to make this an equal sign, and I'm going to make that 25. Now notice it gives a picture of the distribution. So what we're seeing here is we're seeing every single possible number of people, the number of successes, and the corresponding probabilities. The height of each bar is the probability that you have that many successes. So the probability that you have 25 successes is the height of this bar right here, the one shown in red. And it's not easy to see exactly what its height is. I can see it's around 0.04 by looking at the graph. But if you look down here, it gives the, well, almost an exact value. This is probably rounded to 7 decimal places. I don't know if this is exactly right, but it's pretty good approximation, right? It goes to 7 decimal places. And so that's what I write as my answer, 0.0405. Let's go to 4 decimal places. Approximately 0.0405. That's our probability. Okay? Let's look at the next one. So our next one is, what's the probability that at most 20 adults prefer saving? At most 20. Now, this is where you're going to have to practice interpreting English words into mathematical expressions. What does at most mean? Well, at most means you can get that big, but you can't go over that amount. Well, that's the same thing as saying less than or equal to. So what we're really looking for in part B is we're looking for the probability that x is less than or equal to 20. Okay, so we're going to use the same distribution, but we're going to put this in there. Okay, so let's go ahead and do that. Here we are, same distribution, got the same n, same p. I'm doing less than or equal to 20, so I'm going to make that a 20. I'm going to make this a less than or equal to sign. And there it is, 0.003, and if I round this, it's 0.0034 is my answer. So that's approximately 0.0034. Okay. Part C. Let's go to part C. The probability that more than 30 adults prefer saving. More than 30. Well, what does more than mean? More than means greater than, right? So for part C here, we're looking for the probability that x is greater than 30. And we want to know what this is. Okay, so we're going to go to StatCrunch. And what we're going to do is put a 30 here and put a greater than sign. And there I see the probability, 0.4465. 0.4465. Oops. 4465, right? That's our probability. And you should always round these, I think, to at least 4 decimal places. Even better, go to 4 significant figures. So go past all the zeros. You may need to go to 4 non-zero digits to get these to be marked correct in the homework. Okay, so that's our first example. Let's go to the next one. Oops, we're not there. You're not seeing what I'm seeing. Okay, here's the next one. Assume the probability of a defective computer component is 0.02. Okay. Components are randomly selected. Find the probability that the first defect is caused by, okay, we got the 7th component tested, one of the first 4 components tested, or a component tested after the first 3. All right, a little typo, I should say tested. What kind of distribution is this? Well, let's look at what we're doing. We have a probability of a given component being defective, right? So that's our, where is my screen here? The probability is 0.02, okay? Components are randomly selected. Do we have a fixed number of components? Are we limiting ourselves to only choosing 10 components? No, we're not limiting ourselves to any number of components. We're just going to keep choosing components until we find a defect. So there's no n here, right? So this can't be binomial. And if you just keep repeating the experiment over and over and over again, not a fixed number of times, you just keep going until you get a success. And what you're doing is you're counting the number of trials until a success. That's called the geometric distribution. This is going to be a geometric distribution. Okay, and x represents the number of trials until a success. In the binomial, it was the number of successes. Here it's the number of trials until a success. So when I read this, that the 7th component tested is the first defect. So in this case, a success is actually getting a defect. Sounds a little weird, but that's how we're treating it, right? So this is the probability that x equals 7. Sometimes we might just write this p of 7. Okay, so we're going to see if we can get the measurement for this. This one's actually really easy to do with a formula, but we're using StatCrunch here, so let's do it that way. So we said it's geometric, so what we're going to do is we're going to go get our geometric distribution here. So let's get rid of this one. Go to Stat, go to Calculators, and this time I'm going to choose geometric. Now, we're counting the number of trials, right? So choose that, right? You'll always be counting the number of trials in our problems. And we said the probability of success was 0.02, And we want the probability that x equals 2. Oh, 7. We had 7. Now this one, this one's really hard to see what's going on here. There's actually a whole bunch of bars. They're just so close together that it's just kind of filled in the space. But there's actually a whole bunch of distinct bars, one for each number. All right, we want the probability of 7. Well, you can't really see it in here, but you can read it right off here. The probability that x equals 7 is 0.0177. 0.0177 approximately. Okay? So let's go back and look at the next problem, next part of this problem. What's the probability that one of the first 4 components tested causes the first defect? One of the first 4. So that means that our success, our first defect happens, the number of trials up to that point must have been less than or equal to 4, right? So we're looking at the probability that x is less than or equal to 4 here. So that's what we're going to plug in. Okay, so same distribution. We're doing less than or equal to 4. Let's compute that. And I see the probability here of 0.0776. Okay, so that's my answer. I'm rounding, so I'm going to write approximately equal to 0.0776. Okay, let's do the next one. The next one says, find the probability that the first defect is caused by a component tested after the first 3. So that means how many tests did we do? Well, we must have done at 3 or after 3, more than 3, right? So, sorry, I had a little brain fart there. Okay, after 3. Okay, so after the first 3, it means the number of trials must have been more than 3. Okay, so let's go here. And we're going to put more than 3. Okay, there it is. 0.9412 if I round. 0.9412. Okay, and what it's done is it's shaded everything after 3 red. So you can see there's the numbers, less than or equal to 3 are the black bars, but every other bar has been shaded red, and it's added up all those probabilities, and that's what we get. Okay, so that's the answer there. Okay, let's look at the next problem. A bank expects to receive 6 bad checks per day on average. On a given day, what is the probability of the bank getting? Okay, well, here's our questions. So what are we given here? We're given the average number of checks that are bad per day. When you're given the average number, they typically, for this distribution, I haven't told you what it is yet, they're going to use a lambda here for the average, although you could write a mu, it doesn't matter. The average is 6. When you're given an average amount and you want to know the number that actually happens, just given the average, you're using a Poisson distribution. Okay, and what is x measuring? It's the number of successes again, which in this case a success is a bad check. Sounds funny, but that's how we're measuring it. Or you could also say a number of occurrences. Maybe that's a better way to think about it. Number of times something occurs. Okay, so how many times does a bad check occur? So the first one says exactly 4. Well, that means we're looking for the probability that x equals 4. Or you might write it just probability of 4. So we want to know what that is. So let's go to StatCrunch and get our Poisson distribution. Okay, so I'll close this one down, go to Stat, Calculators, Poisson. And here it is. We got to put in our parameters. Our mean, there's only one parameter for this one, it's just the mean. Put that in. And we want the probability that x equals 4. That's the height. Sorry, you didn't see what I was doing. I put a 6 in for the mean, and I'm looking at the probability that x equals 4. And so that's the height of this bar here. Okay? And we can see the probability is 0.1339 approximately. Okay. All right, let's look at the next one. It says, sorry, my screen's on the other screen, so I can't. Oh, I haven't switched this over yet. That's why. There we are. It says, what's the probability of a bank getting fewer than 5 bad checks? Well, fewer than means we're looking for the probability that x is less than 5. Fewer than 5, less than 5. So I want to approximate this. Okay, so I'll go over to StatCrunch, and let's see what we can do here. Same distribution. I got the average is still 6 here, but I'm going to do fewer than 5. So you see what it did is it shaded in all the bars that are to the left of 5, and it's adding up those probabilities. When you add up those probabilities, you get 0.2851 about. 0.2851. Okay. And our last one here, more than 8. More than 8. Well, that's the probability that x is greater than 8. Okay, so let's go to our distribution calculator here. We want 8, we want greater than, and here it is, 0.1528 if I round. 0.1528. Okay. So one of the tricks in doing these problems is determining what kind of symbol to put here. Is it a less than or equal to, greater than or equal to, or just an equals? If you see the word exactly, then it probably means equals. If it's at most, well, then you're going to have an inequality. If it's more than, you have an inequality. And some of these words mean greater than or equal to, some of them mean greater than. You know, you have to get good at that, recognizing which one it is. Okay, but that's it for this video. Hope that was useful for you. I'll catch you in the next video.